We are doing an experiment called the Light Microscopy Module biophysics-free experiment, and it's an experiment that involves crystal growth. We do the experiments on the International Space Station because it takes time to grow a crystal. When we grow a crystal on the ground, it can take from days to weeks or even months. There's only a few opportunities to do experiments in the acceleration-free environment of space. To get that kind of time frame where you need days or weeks or even a month of time to grow something in that environment, the only capability available to us is the space station. If you go into a pharmacy and get a drug, almost every single drug has been developed through the process of looking at what that drug interacts with. Drugs are very small, the machines in the body that they interact with are also very small, and to look at them we can't use a regular light microscope, we have to use a process called crystallography. As the name might suggest, crystallography involves crystals. And when we grow crystals in space, oftentimes we get crystals that are of much higher quality. And when we have higher quality crystals, we get more information, we get more detail, and we can design new pharmaceuticals faster or better. Now, not all proteins that we send into space grow better. And we have a process on the ground where we believe we can identify which proteins will benefit from microgravity and which proteins won't. And that means that instead of sending 100 proteins into space and getting good results from a few of them, we could send 100 proteins into space where every single one of them would produce results that benefit health on the Earth. And what we're doing is using the Light Microscopy Module on the space station to actually study the crystals as they grow. Now, some crystals that don't benefit from microgravity, are like building blocks, and they'll grow just as well on the ground as they will in space. Some of them are more like jelly beans, and those are the ones that benefit. If we tried to build a wall of jelly beans on the ground, it would fall over. When we build that similar wall of jelly beans in space, and we extend that wall to 3 dimensions, we get a crystal. And that's where we get the advantage of using microgravity to grow crystals. And that's what our experiment is about, using a microscope on the space station to see whether we've got building blocks or jelly beans. And then from those observations, using techniques on the ground, which we can predict that and then send up just the jelly beans and not the building blocks. Every pharmaceutical that you take today is helped by a process called structural biology. What we do is we look at the molecules of life on the very, very smallest level, the same level that pharmaceuticals act on. And if we can understand life in more detail, which we hope to be able to do from the crystals that are grown in space, we'll be able to build those pharmaceuticals or design those pharmaceuticals much more rapidly. Many things that we can't crystallize on the ground, we have no understanding of how they work at the structural level. If we can crystallize them in space, we get an idea of how they work, and that drives the development of new cures, new understandings. So what we're doing is developing a tool which can be used by a lot of different people to ensure that space is used efficiently and effectively.